Okay. Yeah, thanks. Hi everyone. I'll be talking about radiated transfer of Lyman-alpha photon with realistic gas physics. This work was done in collaboration with Girish Kulkarni and Thibaut Garrett. I'll be following this outline for the talk today. I'll cover the context and motivation. Then I'll give details of the methodology, the results, and then finally I'll summarize my results. I think this was already discussed in previous talks, but I'll just use this to set the context for my main results. Uh, so, uh, Sorry. Yeah, so the 21 centimeter signal is a differential brightness measurement of the distortions in the background photon due to the intervening hydrogen, the hyperfine transition in the intervening hydrogen. The main expression for the signal is given by this expression at the bottom, where XHI is a neutral hydrogen fraction, delta is the baryon over density, Z is the redshift, TCMB is a background temperature, and TS is a spin temperature, which quantifies the relative population of the hyperfine levels. Now, at cosmic dawn, the spin temperature is given by a weighted average of two temperatures, the CMB temperature and the gas temperature. And the weight factor is X alpha, which we call the Lyman alpha coupling. So if Lyman alpha coupling is zero, the spin temperature is same as the CMB temperature, in which case there is no 21 centimeter signal. On the other hand, if it is extremely large, then spin temperature approaches the gas temperature, and in that case, the signal is expected to be strong. So now you can see that the signal strength is tied to the accuracy of the Lyman alpha coupling. So in some sense, Lyman alpha coupling is the most important, the critical ingredient deciding the strength of the 21 centimeter signal. So just to show you this in with an example. So this is a typical model of the 21 centimeter signal. On the y-axis, I have the 21 centimeter signal measurement in units of millikelvin, and the x-axis shows redshift. So this strong absorption feature that you see in the signal at cosmic dawn period is due to the Lyman-alpha photons. So it is critically important to accurately model this Lyman-alpha coupling, which is this absorption depth is now being targeted by several 21 centimeter experiments. So our the main goal of this is to accurately model the Lyman-alpha coupling, represented here by X alpha. So without going into too much of the details, at a high level, we can understand what this coupling is. So it basically quantifies the scattering rate of the Lyman-alpha photons. So faster the Lyman-alpha photons scatter, the higher is the chance of getting a hyperfine transition, and accordingly, it impacts the 21 centimeter signal. So in some sense, the modeling of the Lyman-alpha coupling boils down to the radiative transfer of the Lyman-alpha photons. So when I talk about the radiative transfer, so we have noted that in previous works have either ignored the random motion of the Lyman-alpha photons, uh, but those that have included the random motion have ignored the medium inhomogeneities. So the fluctuations in the density and the temperature in the intergalactic medium. So we have identified some of these deficiencies, which we have tried to overcome through our simulations. So just to understand what I said through a simple cartoon illustration, in the approximate picture, photons starting from some source are made to propagate in straight lines through the intergalactic medium. But we know in a more realistic scenario, the photons are expected to do a kind of a random walk through the intergalactic medium. So we expect a decrement, a sort of a decrement in the Lyman-alpha coupling, and sort of bunching close to the sources instead of a uniform Lyman-alpha coupling map. So this bottom picture is what we want to capture through more accurate modeling of the Lyman-alpha coupling X alpha. So let me now talk about the methodology. Instead of solving the radiative transfer equation in a brute force method, we take a Monte Carlo approach to the radiative transfer. In this approach, instead of solving any differential equations, we track individual photons throughout the journey and accordingly find out the total the total Lyman-alpha background throughout the box. So we repeat this process for a large number of photons in order to reduce Monte Carlo noise. So just to see this in action, for every test photon that we send in the simulation box, the photons are emitted from some source. We propagate them and we scatter them. So after scattering, they are made to propagate, and then they scatter and they propagate. So this cycle is continued until the photon has redshifted enough, uh, and as a result, the photon can no longer interact with the hydrogen atom, or in other words, we say that the intergalactic medium is now transparent. So at that point, we break the cycle, and we repeat this whole process for a large number of photons in order to reduce the Monte Carlo noise. Now, this process, this approach that I have outlined is not, of course, not new, and it has been used in several models, different models throughout the years. But what is more special about our simulations in the context of 21 centimeter calculations is that we account for variations in the gas density, the bulk motion of the gas, and the gas temperature. So previous work, like I said, have ignored either the random motions or those that include the random motion, then ignore the fluctuations in the gas density, the bulk motion, or the temperature. That was about the methodology. Let me now show you the results of doing a self-consistent radiated transfer simulation. So I'll be showing these Lyman-alpha coupling maps. So on the left-hand side is the Lyman-alpha coupling map without the multiple scattering effect. So this will show the more traditional calculation of Lyman-alpha coupling. And the right-hand side shows the results from our work with multiple scattering, accounting for all the medium inhomogeneities. So uh, uh, for our simulation setup, our box is 100 co-moving megaparsec H inverse, and this is around at a redshift of 13. So the first image point that you immediately note is that the left hand side, which is the more traditional way of calculating Lyman-alpha coupling, shows a relatively smooth distribution of the Lyman-alpha coupling. Whereas on the right hand side, we can clearly see that there are inhomogeneities and fluctuations across space in the Lyman-alpha coupling. So this is a direct consequence of our simulations which account for the medium inhomogeneities, which was absent in the left hand side. Also note that the overall the Lyman-alpha coupling strength is higher on the left hand side compared to the right hand side. So this is again a result of the accounting of the multiple scattering effects that were taken into account for the right hand side but were absent on the left hand side. We can also look at the corresponding 21 centimeter map. So on the left hand side, we have the corresponding 21 centimeter map for the traditional way of calculating the Lyman-alpha coupling. As a result, like I said, the Lyman-alpha coupling was large. So as a result, the spin temperature is saturated to the gas temperature. So in this case, the signal is in some sense a direct probe of the gas temperature. But this is not the case for a more realistic simulation. which is shown on the right hand side. So in this case, you can see that overall the signal strength is lower compared to the left hand side. So the left hand side, the signal strength is predicted to be larger compared to the right hand side. To give this in some give numbers for this comparison, the RMS difference between these two is about 30%. So clearly, accounting for a more detailed gas physics leads to a significantly different model for the 21 centimeter. Finally, I also want to show you a comparison of the 21 centimeter power spectrum, which is more relevant for the upcoming SKA. So again, for our box of 100 co-moving megaparsec, the corresponding 21 centimeter power spectrum expressed as delta square in units of millikelvin square versus the scale, the wave number k in units of co-moving megaparsec. So you can now see the 21 centimeter power spectrum from our work, the more accurate calculations shown by this blue curve, which is significantly different from the 21 centimeter power spectrum predicted for the case with no multiple scattering. So we can see that there is an enhancement at small k, that is large scales. So this we believe is because of the additional fluctuations in the 21 centimeter introduced by the fluctuations in the Lyman-alpha coupling, which were earlier absent in the red curve. So I think this is where I'll stop, and I'll just summarize. So we have studied the radiated transfer of Lyman-alpha photons at with realistic gas physics. So previous work did not account for the multiple scatterings, or those that account for multiple scatterings did not account for the medium inhomogeneities. Our results suggest that the Lam-alpha coupling map is significantly different compared to the more traditional way of calculating the Lam-alpha coupling maps. And consequently, for 21 centimeter, we note that the global signal differs from the standard predictions by of the order of 30% RMS difference. Um, yeah, so this is where I'll stop, and thank you all for listening.
Thanks, Shikhar. So we can take a couple of questions.
Yes, okay. Thank you for a very interesting talk. I have a question about the power spectra that you showed. Maybe, yes,
Yeah.
this one. So the power spectrum with the radiative transfer simulation has a very clear break at a certain scale, right? You see that it's sort of constant, weakly constant beyond, I don't know,
Yes.
K of 0.2 or so, 0.15, I don't, and then it drops. But is there any physical process that corresponds to that scale? And if so, why is that break missing in the other no multiple scattering power spectrum?
So I don't think it's some special scale. I think this might be partly due to some numerical artifact, I think. But I mean, the main message that I wanted to convey through this that is that there is some enhancement at large scales, the low K values. But but I'm not sure why there should be any special scale at where you see this. So this might be just some numerical artifact.
Okay, thank you very much.
It's the sample variance is going to be very large on those 2 points, and so it should not actually be a break, probably.
Mm-hmm.
Any further questions? If not, then thank our speaker again.
Yeah. Thanks. Yeah.